In this video, we're going to look at how you can convert a given circuit, viewed from the terminals A and B, into its Thevenin equivalent circuit. The idea is to simplify the original circuit so that, from the perspective of the terminals, it behaves in the exact same way, but is much easier to analyze. Now, the Thevenin equivalent circuit consists of just two components, a single voltage source known as the Thevenin voltage and a single resistor known as the Thevenin resistance. These two elements replace everything up to the terminals A and B. Everything beyond these terminals, such as the load resistor, stays exactly the same. It's important to note that this load doesn't have to be a simple resistor. It could also represent a more complex subcircuit. To build this equivalent circuit, we first need to calculate the Thevenin resistance and the Thevenin voltage. In general, it's often easier to start with the Thevenin resistance, since its value is sometimes used in the process of calculating the Thevenin voltage. To find the Thevenin resistance, we look into the circuit from terminals A and B, and we replace all independent voltage sources with short circuits. That simply means we connect a wire across each voltage source, bypassing it. In this particular case, that doesn't drastically change the circuit. However, in a different setup, such as when a resistor is placed directly in parallel with a voltage source, that resistor would be bypassed and ignored when calculating the Thevenin resistance. But in our example, the resistor R1 isn't bypassed because it's still connected into the rest of the circuit in a meaningful way. So let's walk through the process of calculating the Thevenin resistance. First, we look at the resistors R2 and R4. These two are in series, so we add them together to get a new equivalent resistor. We'll call that R24. Assuming R2 is 5 ohms and R4 is 10 ohms, R24 becomes 15 ohms. Next, we take this new resistor R24 and look at it in parallel with R3. To combine these in parallel, we use the reciprocal formula. 1 over the equivalent resistance equals 1 over R3 plus 1 over R24. After doing the math, this gives us an equivalent resistance of about 1.76 ohms. Finally, this parallel combination is in series with R1, so we add R1 to the result. Assuming R1 is 5 ohms, we add that to the 1.76 ohms we just found, which gives us a total Thevenin resistance of 6.76 ohms. That completes the first part of the process. Now let's move on to calculating the Thevenin voltage. This is the open circuit voltage across the terminals A and B. In other words, the voltage you'd measure if there were nothing connected to the terminals. To calculate this, we can use the voltage divider rule. The voltage at the terminals is equal to the source voltage multiplied by the resistance of the parallel network, divided by the total resistance in the path. In our case, the total resistance is just the Thevenin resistance we already calculated, 6.76 ohms. The resistance of the parallel network is the 1.76 ohms we found earlier. So we multiply the source voltage, which we'll assume is 10 volts, by 1.76, then divide the result by 6.76. This gives us a Thevenin voltage of approximately 2.6 volts. Now that we've calculated both the Thevenin voltage and resistance, we can construct the full Thevenin equivalent circuit. From the perspective of terminals A and B, this new simplified circuit behaves exactly the same as the original. That means that whatever is connected beyond those terminals, whether it's a resistor, a more complex load, or an entire subnetwork, will respond in the same way as if it were still connected to the full original circuit. So that's it for this video. Thanks for watching, and make sure to check out my other videos, which also feature more complex circuits with source conversion.